Yeah, hi everybody. My name is Duncan Axisa. I'm a program manager at CW3E, and most of the work that I do is related to FIRO project management. So thank you for having me here. In this short presentation, I make an attempt to present a vision for an improved decision support system. My presentation here is very high level, and it is based on 2 points. One, finer spatial and temporal scale in meteorology and hydrology forecasts, and second, an improved framework. The figure on the right is actually from Martin Clark's group at NCAR, a former lab that I used to work at. And I'm going to use this as a backdrop to make my point. It shows timescales and space scales of several hydrometeorological processes ranging from boundary layer convection and soil drainage in the field scale to synoptic weather and river basin scale. The FIRO forecasting challenge is not to simply provide information based on a model with default parameters, but to provide credible information that matches the actual situation in the field that we have in the FIRO environment, where the temporal resolution is consistent with the spatial resolution of the hydrometeorological processes. The figure shows that there is a general tendency for the temporal processes to decrease with the spatial process scale, although there is quite a broad bandwidth, and this is the gray shaded area. One example of this bandwidth is that policymakers might be able to deal with model products at a monthly resolution, whereas reservoir operators expect model products with a daily or hourly resolution. However, increasing the model resolution is not always the solution without characterization of model error. The figure you see here is the work from Laurel Dehaan at CW3E. What Laurel has done here in a very simple way is she used object identification to identify ARs that exceed a certain strength. She used 31 years of West Wharf reforecast data and GEF's control members to define the AR landfall position using ERA 5 reanalysis as truth. The takeaway here is that for a lead time ranging from 1 to 7 days, you have a position error ranging from 100 kilometers to 300 kilometers. So I take that information and I plot it in the time-space scale on the right. You see the red trace here, and I label that AR to show the forecast scale associated with that. I also add what I think the forecast scale is for thunderstorms based on previous experience. I extrapolate a forecast scale polygon for meteorological models. I add a hypothetical polygon for hydrological models here. This is a less educated guess, as I have not done my homework here. So we have a hypothetical forecast scale space, and if done more precisely, a FIRO decision support system should consider this. The blue areas that are shown here in the space indicate the temporal and spatial resolution at which meteorological models are most commonly applied. This is indicated by the space A, which we could argue is the existing capability ranging from daily to S2S scale. The arrow pointing downwards to space B shows the ambitions of spatial hyper-resolution modeling, where an improvement in skill leads to predictions at finer spatial resolution. The dashed arrows pointing downwards and in the diagonal are an improvement in skill, which leads to predictions at finer spatial resolutions. The dashed arrow pointing towards space C shows the temporal and spatial resolution of hyper-resolution modeling if it follows the direction of characteristic hydrometeorological processes. The arrow towards C is an improvement in both spatial and temporal skill. And the question that I ask the audience here, is this the level of skill that DSTs should aspire to for FIRO needs? I think it is important for the FIRO community to go through such an exercise and establish the forecast skill, spatial and temporal scale required. The punchline here is that a vision for an improved forecasting tool should establish a forecast skill requirement and include finer spatial and temporal skill in meteorology and hydrology models. Part 2 of the vision is improved engineering process. The vision for an improved framework is defined as the current system from which the DST will evolve. However, the system objectives and scope are not identical. The system at present uses external information from multiple sources, each with their own interface requirement. Each model used has its own proprietary format and processing method. The information sources and channels use different structures and formats for data elements and communications. This forces the user to consult many sources and to formulate decision criteria manually. And this leads to a stovepiped framework where multiple information is being channeled and bundled, and there's a hindrance to its integration and its presentation to the user. An improved framework has a uniform structure and standard data elements and communication channels. The data elements conform to uniform and defined data structure. In contrast to stovepiping, it's a better framework. Stovepiping practically prevents the creation of a complete and integrated decision support system. An improved framework should rely on an open system for all the information to operate on a single decision support processing application. So what we have existing can be improved. Models should continue to be improved and should be combined in terms of their output and having a common interface. As Roger just said, we can leverage the experience we have here. There is a opportunity for new product development in this area, and that's the area identified as having an openly available standard format. This part of the architecture, I think, does not exist. A processor should be developed that operates on the models using standard formats. The processor produces a data feed with tailored information processing and display. So this is an improvement from the engineering point of view. So there you go. There's a high-level vision for DSTs going forward that has a scientific aspect to it and an engineering aspect to it. Thank you all.